Hey, hi, welcome to another episode of the Depth First Search by Reclaim Protocol. In this episode, we are going to do a follow-up to the previous conversation that we had about protocol design. This is a follow-up, so if you've not watched the previous video, I do recommend checking that out. In this video, we're going to be getting into the implementation and the technical details. And for that, today I have with me Alex, who's the engineer who led all of this effort in implementing the new architecture. So welcome, Alex.
Thanks for having me. Glad to be here.
Awesome. Alex, we should probably just get right into the weeds. If you could help us kickstart this conversation by talking about the upgrade that we've done, right? So we previously had what was called the proxy architecture, and we moved into something called the SplitAEAD architecture. Why did we bother? Like, why did Reclaim Protocol have to undergo an upgrade?
The main idea was that we wanted to eliminate trust in our company. So we wanted our clients to be able to make proofs of the data without relying on something that we control. So that was the main idea and the main design principle of the new architecture.
What is the specific issue that we are trying to address over here?
With the proxy architecture, we controlled the proxy itself. So as long as we are the sole controllers of this entity, we are able to modify or forge the claims. So this is the part where our clients had to trust us.
Previously, people were trusting us, and we could potentially create false proofs. So like Alex would come to Reclaim Protocol, the company, and say, hey, attest this piece of encrypted data, and we could technically attest it, even though it did not come from an official source. So that's something that obviously we do not want. So the upgrade was necessary. Alex, the next question for you is, in this upgrade or in this implementation now, what are some of the components that had to be implemented? Like if there are like a few components that you could lay out so that we can go deeper into each of them, that'd be super helpful.
Sure. So to make this happen, the first thing we introduced is the usage of trusted execution environments. So it's like isolated virtual machines that nobody, even us, can get access to when they run. And so they are protected by a specific hardware like Intel SGX or AMD, SEV, SMP, or whatever. Amazon also has its own like Nitro enclaves technology. So yeah, it's getting pretty common nowadays to use such types of environments for running an isolated pieces of code that nobody from outside can tamper with. Yeah, the main design goal was to implement an uninterrupted chain of trust starting from the hardware that runs the code and ending with the signed claim that the user sees, so that their claim as a company would not be involved in the process of managing or somehow tampering with this chain.
Does that also mean that somebody on the outside, once a proof has been generated, can verify that completely independently without having to talk to us?
Sure, yes. So this architecture involves documents which are produced by starting from the hardware. So AMD or Intel, they do sign our code. They sign the virtual machine kernel, bootloader, all that stuff. And we also have the hashes of this virtual machine images that we also produce. And then it signs the payload. So this way we can attest that the code that runs inside any virtual machine is exactly the one that you can observe from our GitHub repository. So yes, anyone can verify it.
Is there any other component that we should be talking about?
So because we cannot fully trust the isolated virtual machines, the TEs, they have a history of vulnerabilities. We needed to do something about it to be 100% reliable. So a protocol called SplitAEAD was born, and it involved multiple, let's say, two TEs working in tandem. And that also required us to re-implement TLS, not from scratch, but redesign it so that we could interact with its internals.
Why are there multiple TEs? Maybe let's start there. Why are there multiple TEs in this architecture, trusted execution environments in
So
this
there are two TEs with which user interacts during the protocol execution. So one TE holds all the encryption keys. So user himself does not know the encryption keys that are used for the TLS session. But we need other TE to send the ciphertext, the response that a website provides. We send it to another TE which does not have these encryption keys. So having this separate, we are sure that we don't have to trust TEs with plain text data.
What guarantees does it give with respect to security, privacy, integrity?
If one of the TEs is compromised, then attacker gets nothing because neither of TEs has both the encryption key and the data itself. Either it has the encryption key but doesn't have the data, or it has the data but doesn't have the decryption key. So there's no sense in attacking only one of the TEs.
I also know that the TEs run on different clouds. Why is
Yes.
that?
So if one cloud gets compromised, we can rely on completely different clouds to not get compromised, at least at the same time. So this allows us to diversify the security aspect of all of this. So we don't have to say like, oh yeah, we use TEs, but they both run in the same cloud, like on Amazon or Google or Azure or whatever. So we have one TE running in one cloud, another in another cloud, and not only you need to compromise the hardware that runs them, you also need to compromise the cloud infrastructure, which are two completely different things.
What were the challenges that you faced in running these TEs on multiple different cloud providers?
That's a good question because so we started with AWS and then Google Compute Engine, and they're completely different. At least when we started to look at them, they were completely different in what they offer. Amazon had those Nitro enclaves, which are weird ARM-based solution where you need to like convert Docker images and blah blah blah. So yeah, it was a disaster. Then Google has this pretty amazing thing called Secure Compute Engine, where the only thing you need to do is just upload the Docker image, and it just runs inside the TE. That's basically it. But yeah, Amazon doesn't have it. So we decided to go a little bit lower and work directly with technology called AMD SAV SMP. So it's still a virtual machine. It's not bare metal, but it's based on AMD Trusted Execution Environment technology. And it's both Google and Amazon both provide virtual machines that run on this technology, and other clouds actually too. So it was the easy part. The hard part is that they still have their called trusted platform modules, which are locked and written specifically for each cloud. So Google has its own VTPM module that works with this AMD platform. Amazon has its own TPM module that works with this AMD platform. So what we had to do is to write custom images which don't even have like Linux files. Well, it's just basically it's kernel bootloader, custom bootloader that verifies our code, hashes it, and puts into attestation report. But yeah, so we had to write custom virtual machine images for each of the clouds. But they, as soon as they're done, they become static, and we can pin their hashes if we ever make some changes, updates. So their hashes are changed, and we publish them in our repositories.
So, what were the challenges that we had in getting TAs, not only across clouds, but just the existence of two different TAs to work together?
Yeah, so two different TEs working across clouds or in the same cloud, doesn't matter. They have to somehow trust each other. So we had to introduce mutual attestation for them. When TEs talk to each other, they always verify that they're talking to pieces of code that was proven and pre-approved. So each TE has a hash of another TE, inside. So when they talk, they check certificates that were issued by ITs themselves and signed by the hardware. So this chain of trust is also never broken. So when we only started and worked with AWS Nitro enclaves, there was no way to pass environment variables inside the image externally. So they had to be baked inside the image. So when you run two of these images and each of them has to have the hash of the other one inside, you get kind of a chicken and egg situation. So when you put a hash of something inside the other image, that image's hash becomes different.
That's true.
And then you need to put that image hash inside the first image, and it again becomes different. So you kind of synchronize these two images to contain each other hashes without, I don't know, breaking reality. But we managed to do this by supplying hashes externally via network. So it was just basically it was a hack till we figured out that there were technologies already like Google Confidential Computing or MDC that just simply allow you to pass environment variables externally. And then those variables also get into the attestation report. So you can also check that they were not tampered with. And that was the solution to the problem.
Got it. Awesome. Moving on, one of the larger parts of the implementation was implementing the TLS library from scratch. Do you want to highlight A, what we implemented from scratch, and B, why?
Okay, so we implemented TLS library because we needed to have separate code paths for decrypting website's response and verifying it, so that one TE could independently verify encryption tags, TLS encryption tags, and the other party could generate key stream, which would be shared with the user. So in order to do that, we had to, I wouldn't say like write TLS from scratch. We reused the existing Golang library parts as much as we could. But in the places that required interaction and which the standard library, of course, would never make public, those parts are taken from the standard library and just exposed as public methods so that where needed we could interact with them. But that library, even though it like looks custom, it passes all the standard tests, so it's safe to use. And also,
just to be sure,
yeah,
when you say public and private methods, these are the public and private from the perspective of
code that
the
calls
class
it
implementation, but
yes.
all there's, even when you say it's a private function, it's still like open source, just that it's a private function from a programming nomenclature.
Yes. So Golang standard library, of course, has its TLS implementation, and it's all in the source code. So we didn't need to like re-implement TLS from scratch. We just took the parts that were already there and exposed the needed primitives that we needed for the protocol to work and to use them.
And one of those primitives that the protocol needed was the TLS to terminate inside the TE. First of all, what does that mean and why was it important and what were the challenges in implementing it?
So challenges started again with when we tried to use Amazon's Nitro enclaves because they do not have network per se inside the enclave. All they have is some virtual socket that is only connected to the parent virtual machine that this enclave runs on. So we had to write some proxy that accepts incoming traffic, like normal TCP traffic, forwards it over this virtual socket to the enclave, and then decrypt it inside the enclave. Yeah, that was a pretty big pain. But again, all the other things like Google and AMD, they just have network natively. So there's no problem in accepting network connections from the outside world. The problem was that, again, in order to eliminate trust in our network infrastructure, we needed to terminate TLS inside the enclave so that connection from the client to the TE would be secure regardless of like our certificate management or ability to get private keys from these certificates or whatever to become man in the middle. So TEs, when they boot up, previously they received certificates themselves while Let's Encrypt. Now that we moved to array TLS, they issue certificates themselves and they're signed by the hardware. So we don't need domains anymore or Let's Encrypt, so it's even more secure. So like they're even more self-contained right now. So they fully boot up. They generate their own self-signed certificates, which anybody can verify by following the chain of certificates up to the AMD, Google or Amazon themselves. So it's further isolated.
Talking of chain of certificates, now how is all of this packaged together? Eventually, what we are generating as an artifact is a proof that we share with our customers. How do they verify the proof that we are giving them? I know they don't have to trust Reclaim Protocol, the company, but how can they still verify the proof that we're giving them? And what can they verify?
The full chain. So currently our proofs are signed claims. Each signed claim contain 2 hashes of 2. So 1 hash for each T. This hash is a hash of the executable that runs inside the T. So you have 2 T's, you have 2 hashes. So in order to perform like full verification, you take these hashes, you go to our GitHub, you run the verify script, which does the reproducible build from the same commit that the binary was deployed and prints you the hash which should match the one that you see in the claim. If you want to go even further, you can then analyze the code and extract all the root AMD certificates that sign the hardware. You can extract the hashes of virtual machine images that are also inside the attestation, so you can follow it all the way to the hardware if wanted to.
Perfect. Awesome. And I believe all of this is already published on trust.reclaimprotocol.org where people can go check it out. There's a small tool that's built out over there as well where you can just upload a session and verify the entire certificate chain. Again, for that you need to trust us, but you could probably also run independent scripts which are also available on that same portal that you can download, vet, and run it by yourself on your command line.
Yeah, it just automates the process that you can do manually. It takes your claim, checks the hashes, whether are they in that published hashes file, and if they match, then all's good.
Awesome. That covers all of the components that we had discussed earlier on. Alex, as a closing question, what in the development of all of this were you benefited by AI for, and let's just call it, where did it not help as much?
Implementing cryptography like new crypto primitives is not AI's strongest part. Even the latest AI models, they drift away from the original goal that you set up. They drift away very easy because they don't have like anchor to rely on. So whenever you do like really something, that's kind of when you have to always direct them along the way. And where that it was easy, like relatively easy when I needed custom VM images for booting the TEs with AMD. Then the AI knew like what needs to be done and pretty quickly came up with a working solution. But everything related to like completely like something that's never been done in related to like mathematics, cryptography. Yeah, that's where manual still lots of manual interaction is required. That would not something I would trust AI still to do.
Not yet, not yet. Awesome. This was a great conversation, Alex. Thank you so much. That was the end of the questions that I had for you. All of what we discussed today is live and in production. So if you're using Reclaim Protocol in any form or shape, you've probably already been using all the architecture that we just talked about today. Alex, thank you so much for taking time to dive deeper into the implementation details. where can they find you on social media or contact? How can people reach out to you if they have questions?
I'm available on LinkedIn and on Twitter, probably Telegram sometimes.
We'll put in the links to those in the description of this video.
Thank you for having me.
Awesome. Thank you so much. Thanks, folks. Bye.